Okay, so here's another rearrangement, and this one involves what looks like a ring expansion. So it's actually asking us to follow the flow of electrons here, shown here, these pink arrows, and show the structure of the carbocation intermediate here. We're protonating this double bond, but other stuff is happening. So we know that this is a carbocation of some sort, and then bromide adds to that to give the final product. So what are they? What is the carbocation and what's the final product here? So we would normally just protonate this double bond and put a carbocation there. Whoops. But it's actually showing us that not only are you protonating the double bond and losing bromide here, but also you have this flow of electrons from, let's just number these carbons, 1, 2, 3, 4, 5. So you have a bond between 5 and 3, and that sigma bond, these sigma electrons are moving over to essentially kick out these pi electrons here, and those pi electrons attack the proton and then bromide leaves. So this is happening all in one step. At least that's the mechanism as proposed here with these curved arrows. And I'm just going to redraw what you get when you do that, and I'll draw it in the same kind of way. So I'll have, let's just put the starting material here, and when we HBr, when we follow the flow of electrons here, so again, this is the flow of electrons, we will essentially end up with a proton attached here. This is H. And now this bond, I'm going to just erase it, and I'll make a new bond here and a carbocation there. So let's just number these carbons again. We had 1, 2, 3, 4, and 5. So now notice this bond between 5 and 3 is now a new bond between 5 and 2. And then we protonated on carbon 1. So that you could also think about that as having arisen from this carbocation there. If we had just followed this, if we had just followed this curved arrow and this curved arrow, we would have generated this secondary carbocation here, and then we could simply do this sigma shift. It's like a methyl shift or a hydride shift to get here. But according to this mechanism as written, it all happens in one step. Now we can redraw this. So this is these are 4 carbons, 2, 3, 4, and 5, in a ring. So let's redraw that as a 4-membered ring, as a bona fide 4-membered ring. So I'll draw my 4-membered ring, and let's number the carbons again. It always helps to number the carbons. So 2, 3, 4, and 5. That way it'll help you get your bearings and help prevent mistakes. So we know that carbon 2 has this carbon 1 attached, like that methyl group, and then carbon 3 has a carbocation. And so that is our carbocation intermediate. And when bromide adds, Br minus, so let's just add Br minus to the carbocation, and we end up with a ring expanded product. And the driving force for this, the driving force for the ring expansion here, is probably the relief of the ring strain inherent in a cyclopropane ring. So there's quite a bit more ring strain in a cyclopropane than there is in cyclobutane. So that's a ring expansion that's carbocation driven, but it's very much like a methyl shift or a hydride shift.